Welcome to another video in a series on the RISC-V architecture. In this video, I'll introduce and describe the Physical Memory Protection System. In summary, this system allows code running in machine mode to impose access privileges and constraints on regions of the address space. And this is the physical address space, so it can be used to protect main memory as well as read-only memory and I/O devices, which are memory mapped into the address space. The Physical Memory Protection System works by dividing the address space into a number of regions and imposing read, write, and/or execute permissions on each region. The kernel and any other code running at the supervisor or user mode privilege level is checked, and any violations will cause access fault exceptions. The system might be used by a hypervisor running in machine mode to host multiple guest operating systems simultaneously, each running in supervisor mode. It could restrict each operating system to certain areas to make sure they don't interact with each other. The physical memory system might also be used to implement secure booting, real-time operating systems, and other security infrastructure. Okay, with that introduction, let's get going. To motivate RISC-V's physical memory protection mechanism, imagine that we've got a system running an operating system like Linux. The kernel is running in supervisor mode, and the user processes are running in user mode. Now, of course, the kernel will use the paging mechanisms to implement virtual memory. The paging mechanism and the physical memory protection mechanism are two very different things. A particular RISC-V system may have both paging and the physical memory protection mechanism implemented, or it may have one but not the other implemented. And some simple systems may provide neither paging nor physical memory protection. Machine mode code will be used for booting and startup and to configure and set up the hardware. In order to make the kernel portable, we need to hide as many of the hardware specifics from the kernel as we possibly can. We want to force the kernel to use a standard interface to machine mode code so that the same kernel code can be run without any changes on different hardware platforms. All hardware-specific details should be handled only by machine mode code and should be hidden from the kernel software. Also, to enforce security, we may want to protect certain memory regions and some I/O devices from arbitrary access by the kernel. The hardware platform will have some physical address layout, as shown in this example here. Some addresses will correspond and map to main memory, and it's likely that there's also a region of read-only memory, which would be used for booting, that's mapped into some other location in the physical address space. And we'll have several I/O devices. In RISC-V, all devices are memory mapped, so each device is accessed by reading and writing to specific locations in the physical address space using the load and store instructions. For the purposes of physical memory protection, the physical address space would be broken into a number of regions, and each region would be tagged as either readable, writable, or executable, or maybe none of the above and not accessible at all. For example, the machine mode code might mark itself, which is located here, and the read-only memory, and maybe some devices, as simply not accessible by the kernel. Any attempt by the kernel or user code to access these regions would be disallowed and would cause an exception. The machine mode code might also mark some devices as read-write but not executable, and other devices, perhaps like a real-time clock or some configuration parameters, as read-only. After the machine mode code has loaded the kernel into memory, it could mark the kernel's code as execute only and mark the kernel's data area as read-write. It might do this as a security measure to make sure malware doesn't alter the kernel code or try to execute something that's not legitimate kernel code. The remainder of the memory, where the kernel will be placing the user processes, would be marked with no restrictions. Now let's focus on a single region. For each region, we need two pieces of information. We need to know where the region is located, and we need to know what protections the region is to have. Let's discuss another scenario in which the physical memory protection system might be useful. Imagine a real-time system, such as a computer controlling an airplane or a spacecraft. In order to meet the timing requirements, the system will need to avoid using virtual memory. Accessing page tables introduces too much uncertainty, causing unpredictable delays, so maybe the core would not even implement supervisor mode. Instead, the kernel will run in machine mode, and the application processes would run in user mode. Each application process would be placed in its own fixed region of memory. The key requirement is that processes must be isolated, and any failure or malware in one process must not corrupt the other parts of the system. The approach would be to put the kernel and each of the application processes into its own individual region. Before running any one process, that is, before giving a time slice to any application thread, the kernel would set the physical memory protection system up in order to allow only access to the region associated with that process, thereby protecting all the other regions of the address space. Let's go back to the map of the address space, and let's focus on one particular region. As I said, we need to know where that region begins and ends, and what sorts of operations are allowed in it. To implement this, the physical memory protection scheme provides a bunch of control and status registers, as shown here. Each region will be handled with one physical memory protection address register and one physical memory protection configuration register. The configuration register is only 8 bits, and it has bits for read, write, and execute. There is also a locked bit and an address matching field, but let's ignore those until later. There are 64 of these registers, and so a RISC-V system can accommodate up to 64 different regions. Also, note the names of these registers. The address registers are numbered, and the name ends with the number, while the configuration registers are also numbered, but the numbering is like this with the number in the middle. This confused me at first, and you'll see what I mean later, and for now, just keep that in mind. The system is kind of complicated, but let's begin simple, like this. The boundaries between the regions are specified by whatever's in the address registers. Each region begins at the end of the previous region and extends to whatever its address register contains. Address register N points to the end of region N, and more precisely, it contains the address of the first word just beyond the region. The first region begins at address 0 and extends to whatever the pmpaddr register contains. For 32-bit RISC cores, the PMP address registers are 32 bits in size. But with paging, physical addresses can be up to 34 bits in size, which means a 32-bit core can access up to 16 gigabytes of physical memory. The PMP regions must always be at least word aligned, and since the boundaries must be evenly divisible by 4, the last 2 bits of any address must always end with 2 0 bits. So the PMP address registers contain 32 bits with an additional 2 bits of zeros being implicit, and this is how the physical memory protection mechanism accommodates 34 bits with a 32-bit address register. For 64-bit cores, physical addresses are now 56 bits in size. Since all regions must be at least word aligned, the final 2 bits of PMP addresses are still implicit. So the address registers which are now 64 bits in size, contain the remaining 54 bits. Any upper bits that exceed this, or that exceed the actual address range implemented on the system, are simply ignored. Now let's take a look at the 8-bit configuration registers. On a 32-bit RISC core, all control and status registers are 32 bits in size. For the physical memory protection scheme, 4 configuration bytes are packed into each control and status register. In order to accommodate 64 regions, we need 16 control and status registers, and the configuration bytes are packed into each register, as we're showing here. Each configuration register contains 4 configuration bytes. And now let's look at the names of these registers. You can see that the actual registers have names that end in a number, pmpcfg, and then the number, while the configuration bytes have similar names, except for the number is in the middle. And see how the 8-bit bytes are packed into the 4-byte registers? Notice, for example, PMP-1 config is not in the register with the name pmpcfg1, and this confused me initially. It's very similar for 64-bit cores, in which the control and status registers are 64 bits in size. For these systems, we can now pack 8 configuration bytes into each register. And for 64 regions, we now need only 8 registers. These are the registers that are used to hold the configuration bytes. And notice that we are only using even-numbered names. The other half of the registers, those with odd-numbered names, are not used and don't even exist. How many physical memory protection registers must be implemented? In other words, how many regions can be accommodated? Well, the RISC-V spec gives only 3 options: 64, 16, or none. If the core can accommodate 64 regions, then it will have 64 address registers with these names, and it will have 64 configuration bytes with these names packed into registers with these names here. For systems that implement only 16 regions, we'll have 16 address registers and these 16 configuration bytes. And for systems that don't implement the physical memory protection system at all, none of these registers would even exist. Now let's take a look at the so-called address matching field. This is a 2-bit field with these possible values. So far we've been assuming that it contains 0, 1, which is the code for top of region. For now we'll ignore the locked bit. If the configuration byte does in fact contain the top of region code, then the address registers, which are used to delineate and define the regions, are interpreted exactly as we described previously. In other words, region N will extend from the address in register PMP address N-1 to the address in PMP address N, with the first region starting at address 0. With any attempt to access memory, or to access a memory map device, either with a load, a store, or an instruction fetch, the read, write, and execute protection bits would be checked. If the corresponding bit is 0, then the operation will not occur and an access fault will occur instead. For example, an attempt to load from a region not marked readable will cause a load access fault. And similarly, for store instructions to regions that are not writable, or attempts to execute code in a region that is not marked executable, we would get an access fault. Now, in previous videos, I was a little vague about access fault exceptions, and now you know what can cause such an exception. These protection bits are only checked when executing in supervisor mode or in user mode. Machine mode code has full privileges and no checking is done. Now let's look at some of the other codes for the address matching field. First, we could use the code for OFF if we just wanted to use the corresponding address register to specify the starting address of some region, where the following register would contain the top of region address. Now you might think you could just specify a region with no privileges to achieve the same effect, but there are some subtleties. And by the way, this whole video should probably be viewed as an overview and an introduction to this subject. Anyone actually coding this stuff should probably force themselves to plow through the RISC-V specification. Another code, 10, is called NA4, Naturally Aligned 4-Byte Field. If the configuration byte contains this code, then the region will only be 4 bytes in size. This might be useful for protecting an individual I/O device register whose size is a single word. The address register would contain the address of the word to be protected. And recall that the final 2 bits are implicitly zeros, forcing the address to be a word-aligned address. This last code, bits 11, for naturally aligned power of 2 region, is used to specify regions whose size is, well, you guessed it, a power of 2, and starting with 8. So the region size is either 8, or 16, or 32, and so on. Regions of size 4 were handled with the NA4 code. Okay, so if the configuration byte contains this code, then the hardware will look at the value that's stored in the corresponding address register to determine just how many bytes are to be in the region. The address register contains an encoding of both the starting address as well as the region size. Basically, the position of the rightmost 0 in the register tells just how big the region is to be. And so here are some examples to illustrate how this idea works. If, for example, the first 0 is here, the physical memory protection hardware will understand that the region is to be 8 bytes in size. And with the implicit 2 zeros right here and this 0, the remaining bits give an address which is evenly divisible by 8. So it's an 8-byte aligned address. If you store a value that looks like this, for example, into the corresponding address register, the hardware will see that the first 0 bit is here and deduce that the region is to be 32 bytes in size. And the hardware will then replace all these 5 bits with zeros to give an address that is 32 bytes aligned. So that's pretty cool. As previously mentioned, the hardware will check the physical memory protection registers on every load, store, and instruction fetch when executing in Supervisor or user mode. And if there is a privilege violation, an access fault exception will occur. Of course, the registers could have been loaded with conflicting information and overlapping regions. However, the hardware will always check the registers in order, and the first one that matches the given address will be used. If the address is not within any region, the access is considered to be in violation. The physical memory protection registers are all machine mode registers, even though their names don't begin with an M. So they can only be read or modified by code running in machine mode. So far, we've ignored the locked bit and assumed it was 0, that is, that the registers were not locked. When the region is unlocked, then accesses in supervisor mode and user mode are always checked, but accesses in machine mode are not checked and are always allowed. When a region is unlocked, the corresponding address register and configuration byte can be changed by any code running in machine mode. But once the locked bit is set, things are very different. First, the address register and configuration byte become fixed and can't be changed, even by code running in machine mode. Upon system reset, all the registers start in the unlocked mode, but once locked, they can never be altered. So the region cannot be unlocked, and it'll stay locked until the next reset. Furthermore, once a region has been locked, any and all accesses in machine mode to bytes within that region will be checked, just as they are for supervisor and user mode accesses. So how could this functionality be used? Well, maybe the system needs to allow some untrusted code to run in machine mode. The trusted code might be able to use locking to enforce some degree of security against both buggy code and malware. So this mechanism might be used to try to protect critical code from being corrupted. It might also be used to protect software that is considered to be intellectual property and make it tougher for people to read or modify. So let me mention one other small detail. Locking some particular configuration byte prevents changes to that configuration byte as well as to the associated address register. But if one configuration register specifies a region using the top of region code, then the previous address register, which contains the starting address of that region, also becomes critical. So in this situation, locking such a configuration byte has the side effect of also locking the previous configuration byte. Now we're going to get into even more detail and describe grain size. Up to this point, we've assumed that we can lock individual words, but nothing smaller. In other words, we can't lock individual bytes within a word. All the bytes in the word must share the same privileges. And furthermore, all addresses must be word aligned, and the size of each region must be a number of words. That is, it must be an even multiple of 4 bytes. And we call this the grain size. So far, we've assumed a grain size of 4 bytes. But some systems might not support such a fine-grained control over the PMP privilege system. As an example, we can imagine a system that can support physical memory protection, but only on chunks or blocks of size 256 bytes. Each address must be properly aligned on a 256 byte boundary, and the size of every region must be a multiple of 256 bytes. First of all, when the grain size is greater than 4, the address matching code for naturally aligned 4-byte regions is simply not allowed because the system can't support regions that are that small. Now let's consider our example where the grain size is 256. All properly aligned addresses will therefore end with 8 0 bits as shown here. To determine the grain size of the system, in case it can't be determined some other way, you could write some code. So the idea is to set one of the corresponding PMP configuration bytes to use the top of region code. Then you'll write a value of all 1 bits into the corresponding PMP address register, and then read it back and see what you get. The hardware will zero out the lower order bits to force it to become a properly aligned address. In this case, we read back a value in which the lower 8 bits are zeros, and we can conclude that the grain size is 256. Actually, you'd need to take into account the 2 implicit bits, but you get the idea. And finally, don't forget to properly initialize that region to something else, or at least turn it off so it doesn't cause problems later. Okay, that wraps up my overview of RISC-V's physical memory protection system. In this video, we saw that the system is implemented with a collection of machine mode control and status registers that divide the physical address space into a number of regions. Each region can be tagged as readable, writable, and/or executable. When supervisor or user mode code attempts to use a memory address for which permissions are not granted, then an access fault exception will be signaled. A core may implement up to 64 such regions, or maybe it doesn't even implement the PMP system at all. But if memory protection is implemented, we saw that each region has both an address register and a configuration byte. These describe the address regions. The physical memory protection system can be used in conjunction with the virtual memory paging system. Basically, an operating system running in Supervisor mode will be constrained as to what areas of the physical address space it has access to. So I covered a lot of details, but if you made it up to this point, you now have a pretty good idea of what the physical memory protection system is all about. So let me end by saying thanks for watching, and I hope to see you in the next video in this playlist.